Hello and welcome to this video from Heybridge High School Maths Department. Today we're going to look at part of objective NP 10.3, which is proving two shapes are similar. On the slide here it tells us that two shapes are similar if all the corresponding angles are equal and all the corresponding side lengths are in the same ratio. Now, if you think about regular shapes, so equilateral triangles, squares, regular pentagons, regular hexagons, if you have two of those, they're always going to be similar because you're always going to have the same corresponding angles. I mean, all the angles in these shapes are equal, so no matter how we rotate or reflect them, all the angles will correspond, they'll all be equal, and you'll always have your side lengths in the same ratio because all the sides are of equal length. It's also worth noting that if you're looking at triangles, it's enough to show that all three angles in both triangles are the same, or that all three corresponding side lengths are in the same ratio. So with triangles you don't need to prove both, you just need to show one of the two to show that it's true. So our first question, in the diagram, BC is parallel to DE, and we need to prove that triangle ABC is similar to triangle ADE. So this small triangle at the top, ADE, is similar to the large triangle ABC. So if we have a look, first of all, we've got this angle at the top, and this is angle DAE, but it's also angle BAC, so it's included in both triangles. So therefore we can say that both triangles share angle BAC. Okay, then if we have a look here, we've got parallel lines, so we can use the properties of angles in parallel lines to prove that these other two angles are equal to these. So if we have a look here, we've got angle AED and we've got angle ACB. And those are both going to be equal because they're corresponding angles in parallel lines. And exactly the same thing will happen with angle ADE and angle ABC. Those are also corresponding angles in parallel lines, so those are going to be equal too. So we've shown that triangle ABC and triangle ADE have three equal corresponding angles, so therefore the two triangles are similar. When you do these questions, you will usually be asked to explain your reasoning, so you need to give reasons why the angles are equal. Question, we've got MNO and LNP are straight lines, LM and OP are parallel. Explain why triangles LMN and NOP are similar and give clear reasons for each statement you make. So if we start here, angle LNM and angle ONP will be equal. So we can say angle LNM is equal to angle ONP. Okay, and that is because they are vertically opposite. Okay, if you're doing this in an exam, write slightly more detail. So put something along the lines of vertically opposite angles are equal. Don't just write vertically opposite. So let's have a look at angle LMN and angle NOP. So I can say again, those are going to be equal. So LMN is going to be equal to angle NOP. And if you actually have a look, these are alternate angles in parallel lines. So if you actually if this was an exam paper, if you actually turn the exam paper around, you'd be able to see that they're on opposite sides of line O and M, and you've got a parallel line LM and a parallel line OP. So therefore they are alternate angles and they will be equal. So let's just put alternate angles. Okay, and then finally we've got angle NPO and angle MLN, and those are also going to be equal. So MLN is going to be equal to NPO, and again those are alternate angles. And if you're doing these in an exam and you're a little bit unsure, always turn the exam paper around. A lot of people seem quite frightened to turn their exam papers around. It's absolutely fine. You can turn your exam paper around whatever way you want to so that you can see diagrams more clearly and make sense of them. Look at a question involving two rectangles. So because we're told that these shapes are rectangles, we know that the angle criterion is met. So we've got our 4 equal corresponding angles. So now we need to have a look at our side lengths. So Jim says the two rectangles are similar because 8 plus 4 equals 12 and 6 plus 4 equals 10. Is Jim correct? Explain your answers. Now Jim's adding, and what we're actually interested in is ratio. So let's start off by having a look at the lengths of our rectangles. So my first rectangle has got a length of 8 centimetres and my second one has got a length of 12 centimetres. So the ratio of my lengths is 8 to 12, and I'm going to simplify that as far as I can. So the highest common factor of 8 and 12 is 4. So I'm going to divide both sides of my ratio by 4. That will give me a ratio of 2 to 3 for my lengths. Now if I have a look at my widths, so my first rectangle is 6 centimetres wide and my second is 10 centimetres wide. So if I cancel that down to its simplest form, I'm going to divide both sides by 10, and that's going to give me 3 to 5. Now what I would like is to have one part of my ratio for each ratio the same. So I'm going to have a look at the first part of each ratio. So I've got 2 for my lengths and 3 for my widths. So I'm going to turn them both into 6 to something so that I can compare them. I'm going to multiply both sides of my first ratio by 3 and I will get 6 to 9. Now my second ratio, if I have a look at the original form, it was 6 to 10. So I don't actually need to scale it up again. I can just look at what I originally had. So the ratio of my lengths is 6 to 9. The ratio of my widths is 6 to 10. So Jim is not correct. And we have to put a reason. So what we would say is the ratios of the corresponding side lengths are not equal. So the two rectangles are not similar. Question involving rectangles. Again, are the two rectangles mathematically similar? Tick the appropriate box. You must show working to justify your answer. So let's have a look at the ratios of our side lengths again. Again, we're told they're rectangles, so we know they're the same shape, the angles are the same. So our length, so our first rectangle is 15 centimetres and our second rectangle is 25. And I'm going to simplify that. Highest common factor of 15 and 25 is 5. Divide both sides by 5 and we'll get the ratio of 3 to 5 for the lengths. Now let's have a look at the widths. So my first rectangle has a width of 10 centimetres and my second has a width of 20 centimetres. Highest common factor of 10 and 20 is 10. So I'll divide both sides by 10, and that will give me a ratio of 1 to 2. And then if I scale up this left-hand ratio, this ratio with the width, I can go from 1 to 3 on the left-hand side. So I'm going to multiply by 3 on both sides, and that will give me 3 to 6. So the ratio of the lengths is 3 to 5, and the ratio of the widths is 3 to 6. So we can tick the box that says no, because the rectangles can't be mathematically similar because the ratios of the corresponding side lengths are not equal. We've got another question on rectangles, and we've got a €20 note is a rectangle 133 millimetres long and 72 millimetres wide, and a €500 note is a rectangle 165 millimetres long and 82 millimetres wide. Show that the two rectangles are not mathematically similar. So I always put the measurements onto the diagram, because then I can see a lot more clearly what I'm going to compare. So that's my first note. This is the €500 note, so that's going to be 165 millimetres long, and it's going to be 82 millimetres wide. So let's do exactly what we did in the last question. We're going to compare the length and the width by using ratios, but this time we're going to put them into the form 1 to n. So if I start off with my lengths, I'm going to have 133 to 165, and I'm going to turn that into the ratio in the form 1 to n. So the first part of the ratio will be 1, and I need to determine the second part, which is going to be a number n. So to get from 133 to 1, I'm going to divide by 133, and I need to do the same on the right hand side as well. And 165 divided by 133 is 1.24 to 2 decimal places. Now let's have a look at my widths. So I've got 72 for the €20 note, and I've got 82 for the 500. And again, I'm going to go into the ratio 1 to n. So I'm going to divide both sides by 72. So 72 divided by 72 gives me my 1. 82 divided by 72 will give me 1.14. So we've shown that the two rectangles are not mathematically similar, and you should make a comment here that the two rectangles are not mathematically similar because the ratios of the corresponding side lengths are not equal. So back to triangles. In the diagram below, BC is parallel to DE, and we've got some side lengths on there, and we need to explain why ABC and ADE are similar. So again, we've got this angle here, which is common to both triangles. So in both triangles, that angle would be the same. We've got angle ABC and angle ADE being corresponding angles in parallel lines, so they are equal. And then we also have angle ACB and angle AED being corresponding angles in parallel lines, so those are also equal. So triangles ABC and ADE are similar because they have 3 equal corresponding angles. Now, part B, find the lengths of x and y in the diagram. So here's x is actually BC. So we're going to use the lengths of AB and AD to work out what the ratio of the sides in triangle ABC to those in triangle ADE is. So if we start off with AB to AD, so we can see from the diagram that AB is 12 centimetres. AD is going to be the whole of this length, so it's going to be 12 centimetres plus 8 centimetres, which will give me 20 centimetres. And I'm going to simplify that. I'm going to divide 3 by 4 on both sides. And that will give me a ratio of 3 to 5. So I know that the ratio of the side lengths of triangles ABC and ADE, they're in the ratio 3 to 5. So let's start off by finding x. So x to 25 centimetres, those are in the ratio 3 to 5. So what do I multiply 5 by to get to 25? I'm going to multiply it by 5. That's going to give me 25. So I'm also going to multiply 3 by 5 to get x, and that will give me 15. So x is equal to 15. Okay, so length y is slightly trickier. So we know that the ratio of our side lengths is 3 to 5, and we know that y will represent 3 parts of the ratio, and the whole length AE will represent 5 parts of the ratio, and that will be y plus 10. So the difference between these two expressions, y and y plus 10, is the 10, and the difference between these two amounts of parts is 2. So we could say that 2 parts of the ratio would be equal to 10. So therefore 1 part of the ratio must be equal to 5, because we're going to divide 10 by 2. And then to find the length of y is 3 parts. So we're going to do 5 times 3, and that will give us 15 centimetres. So y is also equal to 15 centimetres. So ABCD and PQRS are 2 triangles. Rectangle ABCD is 15 centimetres by 10 centimetres. There is a space 5 centimetres wide between rectangle ABCD and rectangle PQRS. Are rectangle ABCD and rectangle PQRS mathematically similar? You must show how you got your answer. So we need to work out the length of PQ. And you must remember that we've got this 5 centimetre gap on both sides. Okay, don't think it's only on one side, it's on both sides. So PQ is going to be 5 centimetres plus AB, which is 15 centimetres. So that would be 20 centimetres, and then add another 5 centimetres. So PQ is going to be 25 centimetres. And then the same with QR. Okay, remember you've got that extra 5 centimetres there that hasn't been marked onto the diagram. So for QR, we're going to have 5 centimetres, add BC, which is 10 centimetres, that's 15, and then add another 5, and that will give us 20. So let's have a look at the ratio. So AB and PQ correspond. So the ratio of AB to PQ is going to be 15 to 25. And if I simplify that, that will give me a ratio of 3 to 5. And then let's have a look at BC to QR, because those two sides correspond. So BC is 10 centimetres and QR is 20 centimetres. And let's simplify that by dividing both sides by 10. And that's going to give me 1 to 2. And then I'm going to scale up my ratio BC to QR so that the left-hand side of this ratio is going to match the left-hand side of my other ratio. So I'm going to multiply by 3 so that the first part of my ratio is 3, and multiply the other side by 3 so that I've got 6. So ABCD and PQRS are not mathematically similar. because the ratios of their corresponding sides are not equal. So, final question. A cylindrical bottle can hold 1 litre of oil. A second cylindrical bottle has twice the radius but the same height. It also contains oil. Explain why these bottles are not similar. Okay, so this is going to be my first bottle. And its height is h, and its radius is r. This is my second bottle. Its height is also h, but the radius of this bottle is 2r. So if I was to do the ratio of the radii, I would have r to 2r, which would give me a ratio of 1 to 2, because I could divide through by r to simplify. If I do the ratio of my heights, I'm going to have h to h, and I can divide both sides by h. That's going to give me a ratio of 1 to 1. Now you must remember that the height and the radius are both lengths within this three-dimensional shape. So because the corresponding side lengths are not in the same ratio, then these two bottles are not similar. Thank you for watching.